Hi friends, welcome to follow up. This video is a continuation of problem 268. So in this video, we're going to consider problem 201, bitwise add of numbers range. So we're going to analyze it in certain detail. And first, we're going to use some binary representation to see, to write a solution that will not pass all the test cases. And then we are going to move to the bitwise operations, right? So here the problem states that given two integers, left and right, that represents range left and right inclusive. We want to return the bitwise add result of all the numbers in this range, so inclusive. So here we have three examples. If you look at the last example, right, the right is very large. But if you want to do it in using a for loop or just check every bit, it might have some problem, right? So the second example is very special. So the left and right are the same. So we just return either of them. And the first example, we have 5, had 7. So let's look at the example 1, right? Left is 5, so we're going to do exclusive bitwise add operation for 5, 6, and 7. So if we look at their binary representation, so you are going to see 5 is this is the 4, right? We add 1, so this is the 5. And for 6, so we're going to do this 5 plus 1, that is 1, 1, 0, right? And for 7, so we get so 0, 1, 1, 1, right? So because this bit is 4, and this bit is 2, and this bit is 1. So due to the way of the bitwise add operates, so basically it's the rules of bitwise add. So so we write this, or in Python we can write this add, right? So basically is that if you consider 1 bit position, so you have 1 and you have 1, you're going to result in a 1. All the other cases, you get 0. So in other words, 1 and 0, you get 0. And 1, 0, and 0, you also get 0 for sure. And then the other one, 0 and 1, you get 1. So basically 0 and 1 and 1 and 0, those two basically can derive that the bitwise add is commutative, right? So here, if you generalize this one, you have some bit positions or digits, bit positions. So bit 1 and bit 2 and see bit n. And then if you do exclusive, do add for all of those, right? For all of those things. Then this number is 1 if all bits are 1, right? Otherwise, it's 0, as long as you have a 0. So, right? So this is the same. So here, when we check the positions, the constraint is that left and right is 32-bit integers, right? So we just need to think of 32 bits. And then you check the numbers. And then if one position, you have a 0, and then you just set that bit to be 0. And then you get the result. So let's see. If we do like this, how can we retrieve that? So here I'm going to do an implementation from scratch. So this way I think it will help us understand the logic. So now for I in range 32. The reason is that we just need to consider those 32 bits. And then we want to check if S bit is a set, or in other words, if it is 1 or 0, right? So for this purpose, I'm going to introduce a flag. Originally, I want to set it to be true. And then we are going to iterate over the range. So for y in range, so I write start is left, and the end will be right. So we write right plus 1, right? So now I want to check if the S bit in this current number is 0 or not. If it's 0, we are sure in the final result, so this bit will be 0. right? So we can break. So if not, so let me check the ice bit. So I'm going to do this. So this is basically shift to the right I positions. It's corresponding to integer division y by 2 to the power I, right? Then I do add with respect to 1. So if this is 0, right? In other words, this bit is not set, then the final result, this bit will not set. It remains 0, right? So in this case, I can do the flag to be false, meaning that this position will be 0, right? Then I can actually don't need to consider anymore. So we just break the for block. So then after this, we want to check if flag. So in other words, all the numbers in the range have this current ice bit set. So the final result will be 1. So then we are going to set the result because we are looking from right to left. So this corresponds to 32 minus 1. This is the largest index, then minus I. So we are going to set this byte to be 1. So you can think of this if I equals 0. So we want to set the last element that is at index 31, right? So it's going to be 1. And then we just need to return the result, right? So we want to change this list to be a integer. So this can be done using comprehension. So 2 to the power 32 minus 1 minus I. For example, if I equals 32, that is the last bit, then corresponding to 2 to the power 0, that is 1, right? Then times result I for I in range 32. So this is an implementation. So this is sort of brute force. So though we try to do early stopping and we use so this bitwise operations, so this actual time is not very efficient. So let's do a test. So basically we want to test that the logic is right, but if you do submit, so let's see what we get. It will get time limited error. So now with that, then we want to improve that. In other words, to traverse the range from left up to right is not very good. So now let me copy this part. The first one, so we can use prefix. So let's think of their representation. For example, we have 5, 6, and 7. So as long so we can do from right to left to right. So you have 0, 0, you have 1, 1, 1. So this byte, so up to now, so is this position they have 0, and then this 1. So now if you look at the third bit from right to left, so you have 0 here. So this corresponds to 0, and this last one you have 1, 0, 1. It's also corresponds to 0. So the common prefix, if you regard the binary representation as a string, so it will be 0, 1, right? So the common prefix will be 0 and 1, right? Then we notice that this is at the third bit. So we are going to do, what we are going to do is, so this is the 1, then we actually do this, right? 2. So we're going to have essentially 1 times 2 to the power 2. That is 4. That's also the return. So then we just need to get this prefix, right? So we can check this position. So we just need to focus on 5 and 7. Or if you have a large number, we just need to look at the beginning and the end, and we find their common prefix. So as for finding their common prefix, so we can do division. So for example, if you do 5 divided by 2, you get 0, 1, 0. And 7 divided by 2, integer division, so we get 0, 1, 1. And then you do division again, so you get 0, 1, right? And then you get this one will be dropped, so you get 0, 1. So this will be their common prefix. And then here you do the divisions twice, right? Then we can do this, right? 2, then shift. This is the number of shifts. So basically you do the number of divisions done. right? So we can translate this one into code. So we can do common prefix plus shifting. So this actually is very straightforward. So basically, let's see, we can number of n divisions. So it's 0, right? So basically, while left is less than right. So what we are going to do, we are going to do as long as left. So we are going to do left. So we are going to shift right by 1, right? So we are going to write it like this. This means that left equals left divided by 2. Or you can write in some format like this. Left equals left shift by 1. Same thing, right? But this looks fancier, right? So similarly, we do right shift by 1, right? And then once you do a shift, so basically you number of it corresponds to do one division for each number. So you're going to increment n divisions by 1. So once you exit the while loop, left and right will be equal, right? In this case, the state of divisions is the number of divisions we needed to get them the same. So what we are going to do? So now, so we get they will have the common. This is the common prefix. Then what we are going to do is to return the left, or you can do right? So shift to the left by n divisions. So let's first do a test, and then we make some comments. So let's run this. So invalid syntax. Let's see. I'll put it here, right? Good. It passes the first one. Now let's look at the generic case. Let's see if I want to change this one to be version v1 so that we check this one. Yeah, it passes the first test case. Now let's look at the generic case. It passes. So here actually it corresponds is the same as left times 2 to the power, right, n divisions, right? So this is another solution. So here, in order to get the common prefix, actually we have a better way. So here, let me copy this part. And I'm going to name this one as version v2. So now what I'm going to do is I want to use x and x minus 1. So this, I want to make some explanation here. So given a, say, integer, right? What does, say, I would call it, say, x or n anyway, and x minus 1. What does x minus do? Let's see. So here, actually, it's very simple to digest. For example, let's first try some powers of 2. So, for example, you have 8, right? 8 is 1, 0, 0, 0, right? Then you do 8 minus 1. That is 7, right? So 7, this one minus 1, you will get 0, 1, 1, 1, right? And then you do 8 and 7. You are going to get 1, 0, 0, 0. Not add. So let's see. You are going to get add. You get 0, 0, 0, 0, right? So basically, it actually eliminates this position, right? So now let's look at another one. So you have none, right? That's going to be 1, 0, 0, 1. The 8 plus 1. Now you have 8. 9 minus 1 is 8. You have 1, 0, 0, 0, right? And then you do 9 and 8, right? So you're going to get 1, 0, 0, 0. So in this case, it actually unset the least significant bit, right? So you get 9 itself, right? you're not going to get 9, you get 8, right, in this case. So overall here, in this case, because 8 is a power of 2, right? If I unset this bit, you're going to get 0, right? So in other words, so this x and x minus 1 will unset the least significant bits in the number, right? So if it also can tell if a number is a power of 2 or not. If you have x add with x minus 1 equals 0, it means this x is a power of 2. And otherwise, for general, if this the result of x add x minus 1 is not 0, the role, the effect it plays is to set the least significant bit, right? So this is actually imperfect consistency, because if a number is a power of 2, it only has one bit set as 1. If you unset that one, for sure you get 0, right? So this is exactly the thing we are going to use to get the common prefix. For example, here we have 5 and 7. So we actually can start from the larger one. So as long as the larger one is greater than the smallest one, for example, I unset this least significant bit, so we're going to 0, 1, 1, 0. And then this is still larger than 5 if you compare the binary representation. And then I do it again, so we get 0, 1, 0, 0, right? So I unset the second least to last significant bit. So we get 0, 1, 0, 0. So now this is strictly less than 5, or less than or equal than 5. So this part will be the if we do bitwise add, you are going to get the result. Actually, if this part also suggests the prefix. So now let's look at the code. This role is to unset the least significant bit in binary representation, right? So now what we are going to do, so for I can say nm equals right and left, just right for ease, or you can change left to be m and right to be m. So basically, well, n is greater than m. So what I'm going to do is I'm going to set n to be n at n minus 1, right? So then afterwards, so we're going to get, as we exit this while loop, so n will be less than or equal to m. Then what we are going to do, we just need to return the current state of n bitwise with m. So you're going to get the result. But what you get is not the prefix, but the result. The reason is through unsetting the bits. So actually we get because through this bit, the bits at n will already 0. If you do add, it will eliminate the corresponding ones in the position of m also. So in other words, what we get is the prefix at the right number of zeros, right? So this is the version v3. So now let's do a test. Yeah. So it will pass all the cases and very fast. So here, let me remind you another bitwise operation question, or just this is just a very small quiz. So what does this do? X and negative x. So where negative x is 2's complementary of x, right? Complement, let's see, complement. So you can, this is actually very, very easy. So you can do comparison with nx and x minus 1, and also if you know Fenwick tree, so you can think of its implementation, right? It's in the reason we want you to think of the Fenwick tree implementation is that in the implementation we can use x and negative x, right? So yeah, you can write your answer in below the comment, or you can just do some test to see what you get. So with that said, I guess that's about it for the current video. Thank you.